Welcome to the Unit 2 Discrete Fourier Transform in Digital Signal Processing. Let us start with the session 1. In the session 1, we will try to understand discrete time Fourier transform, its periodic nature, then condition for existence of discrete time Fourier transform, and finally the Gibbs phenomenon. So let us introduce the discrete time Fourier transform first. What we know previously is any signal we can decompose into its elementary signals, and those elementary signals can have different frequencies and different amplitudes. There is a relative phases. So from the Fourier transform, what we can do is we can plot amplitude spectrum, phase spectrum, and those amplitude spectrum and phase spectrum will give you the information about amplitudes and the relative phases of those uh, elementary components. So thus, we are using Fourier transform to convert the time domain signal into the frequency domain signal. So for getting the frequency analysis, we should first convert the time domain signal into the frequency domain signal, and for this convergence, we can use different frequency transformation techniques. So very first, we'll try to understand is the DTFT, that is discrete time Fourier transform, and the expression for this discrete time Fourier transform is nothing but x of omega is equal to summation n runs from minus m to plus m t x of n e raised to minus j omega n. So here x of n is the finite energy discrete time signal, and this finite energy discrete time signal will have its dt of t as x of omega. So finally the expression is what? That is x of omega equal to summation of x of n e raised to minus j omega n, and this is nothing but the equation for the DTFT. We can see it as the analysis equation also. So in other words, you can say that x of omega is the decomposition of x of n into its frequency components. Let's go towards the next point, that is the periodic nature of x of omega. Then what we know is the equation for the DTFT, that is discrete time Fourier transform, that is x of omega equal to summation n runs from minus m to plus m into x of n e raised to minus j omega n. And what we have seen in the previous unit is that for continuous time signal, the spectrum is having its range, frequency range from minus m to plus m t, while for the discrete time signal, the frequency range for the spectrum is from minus pi to plus pi, or you can see it as from 0 to 2 pi. So we can say that this x of omega becomes a periodic with the period 2 pi. If this x of omega is periodic with the period 2 pi, means this x of omega and x of omega plus 2 pi must be same. Okay, means x of omega plus multiples of 2 pi and x of omega must be same. So that's what we try to prove here. So we'll replace, or we'll substitute here omega plus 2 pi k instead of this omega. Similarly is the case for this omega. We will replace this omega with omega plus 2 pi k, and we can write the same expression, this above expression we can write as x of omega plus 2 pi k. We can replace this omega with omega plus 2 pi k is equal to summation of x of n e raised to minus j. This omega is replaced with omega plus 2 pi k, and this n. So now this e raised to minus j omega n and e raised to minus j 2 pi k n, I can separate it out. So after separating, what you will get is the summation and x of n will be as it is. This term will be separated, so it will be e raised to minus j omega n first, and second it will be e raised to minus j 2 pi k n. And what I know is this e raised to minus j 2 pi k n is nothing but cos 2 pi k n minus j sin 2 pi k n, and cos 2 pi k n is nothing but 1, and sin 2 pi k n is nothing but 0. So ultimately this e raised to minus j 2 pi k n would be equal to how much? 1. So ultimately this expression will become this x of omega plus 2 pi k. I can write it as it is, summation x of n e raised to minus j omega n, I can write it here, and this e raised to minus j 2 pi k n is going to be equal to 1. So ultimately, what right hand side I'm getting is the x of omega. So ultimately, I taking what I can write further is this x of omega is equal to x of omega plus 2 pi k. So this proves that this x of omega is having a periodic nature with a period 2 pi. As we can find out x of omega from x of n, I can also find out x of 1 n from this x of omega. And how can I find it is with the help of this expression, x of n is equal to 1 upon 2 pi integration minus pi to plus pi x of omega e raised to plus j omega n d omega. So this equation is referred as a synthesis equation, or you can say it as the inverse discrete time Fourier transform expression. So what we can conclude here is the x of omega is having a periodic nature with the period 2 pi. Now, next is the condition for existence of Fourier transform. So, condition for the existence of Fourier transform is that the discrete time signal must be absolutely summable. Means the discrete time Fourier transform is convergent only if the summation of x of n is less than infinity, that is, it is finite. So that is nothing but Fourier transform or discrete time Fourier transform exists only if discrete time signal is absolutely summable. Next, we'll try to understand the Gibbs phenomenon. What I know is the discrete time Fourier transform, that is x of omega is equal to summation x of n e raised to j minus j omega n, and I can multiply both sides with the e raised to minus j, sorry, e raised to plus j omega m, and I can integrate both sides over the period minus pi to plus pi. So if I'll uh, do the operation on the left hand side, what you'll get is integration of x of omega e raised to j omega m d omega, and on the right hand side I can write here integration minus pi to plus pi summation of x of n e raised to minus j omega n e raised to j omega n d omega. So that is what I have written here, x of omega, its integration, its multiplication, and this right hand side in this square bracket, its integration, its multiplication. Once I got this, I can interchange this integration and summation, and this interchanging of integration and summation is possible only when this xn of omega converges with the x of omega. Okay. Means xn of omega must be similar to this x of omega, and this uniform convergence is assured or guaranteed if x of n is absolutely summable. That is, mod of x of n, summation of mod of x of n must be less than infinity. So the basic difference in between xn of omega and x of omega is that x of omega has infinite limits. X of omega has infinite limits, whereas xn of omega has finite limits. Okay, so that is what is the difference between xn of omega and x of omega. It means that what we are doing is we are truncating the x of omega to get xn of omega. So as we are truncating the original spectrum, we may have a slight difference between xn of omega and x of omega. And if you want to match this xn of omega with the x of omega, what is the necessary condition is that my capital N must tends to infinity, means capital N must be as large as possible. So we'll consider one case in which we'll consider a discrete time signal, we'll consider its frequency domain representation. So we'll consider first discrete time signal. Let us say the discrete time signal in the as a sinc function. So sinc function in discrete time uh, we will consider, and then it's as it is a sinc function, its frequency domain version will be a rectangular signal. As this is a sinc function and it is in discrete time, if it is in discrete time, my spectrum must be periodic. Okay, so this spectrum which I'm getting, that is the rectangular pulse, it is periodic, means it is from minus pi to plus pi, again from pi to uh, 3 pi or 3 pi to 5 pi, the pulse will repeat. Or here from minus pi to minus 3 pi, minus 3 pi to minus 5 pi, the pulse will repeat. So if the time domain signal, it is in discrete time, whatever the spectrum I'm getting, it would be in periodic nature. And if the time domain signal, it is of aperiodic nature, my frequency domain signal would be in the continuous time nature. Okay, so that's what is the relation between the time domain and the frequency domain. So if the signal is discrete in time domain, then frequency domain representation would be periodic. And if the signal is aperiodic in the time domain, then the frequency domain nature would be continuous. So let us go further. So if I'll truncate my Fourier transform, then what will I have is I can observe a oscillatory behavior in the xn of omega at the point of discontinuity in x of omega, and this phenomenon is referred as a Gibbs phenomenon. Let us try to elaborate it. So we'll consider the two figures here. We will have the comparison between the x of omega and xn of omega. In the previous slide, we have seen x of omega, and that is of a rectangular pulse in frequency domain. And if I'll go here, and if I'll observe the uh, figures corresponding to this xn of omega, so here I will get the first figure, which is where the n, capital N is equal to 1, capital N is equal to 3, capital N is equal to 7, 15, 50, and then 17. Then what you can observe here is that I'm having the oscillations here. Here I can see the oscillations in all the cases as my capital N is increasing from 1 to 3, 3 to 7, 15, 50, and 70. This number of oscillations also increases, but whatever the overshoot I'm getting here, whatever the overshoot I'm getting for n equal to 3, for n equal to 50, and for n equal to 70, all those overshoots, the amplitude of those overshoots are going to remain the same. So the same thing I will just mention here, that we observe that there is a significant oscillatory overshoot at W equal to WC is this point. This is the point where you can see that this is my WC point and this is my minus WC point. Similarly, I can write this as WC, I can write this as minus WC. So at WC, I'm having a significant amount of amplitude in overshoot. Here also I can observe the same or similar amplitude for the overshoot. So let me clear these annotations. Yes. So what we can further observe is that as n tends to infinity, the oscillations becomes more rapid. Means if it is n equal to 1, the oscillation is a single oscillation. If I'll go here 15, so I will have some more oscillations. If it is n equal to 50, I will have much more oscillations. And at 70, again, I'm having the increased number of oscillations as I'm going towards the higher number of capital N. But the overshoot of amplitude does not go to 0. Means whatever the overshoot I am observing here, whatever the overshoot I have observed here, its amplitude is remaining the same. And that is what is the Gibbs phenomenon. Okay, that's it for this session 1. And in next session, we will try to understand the frequency domain sampling and the reconstruction of discrete time signal. Thank you.